Thank you, Tom, and thank you to the organizers for inviting me and putting together this very interesting session. What I will try to address in this brief talk is the details and the kind of attention we need to pay to accessibility when we're talking about pedestrians in urban environments, the scale where which they can directly perceive the urban environment. And I'm also going to evoke a sort of an issue with some of the accessibility indexes that pertains to where we assume people to come from when they go to amenities. There's been quite a lot of talk about how accessibility can be addressed by changing destinations, bringing destinations closer to people. But the results obviously also depend on where we assume people start their trips. And I'll expand on that nuance and try to describe how this could lead to different results and different actionable policies if we change our assumption about trip origins. So generally, there are two common ways of approaching destinations when we're in the city. Quite often we do it from fixed locations. Those might be our homes, but they might well be also jobs. And then somewhere in between and around these fixed destinations, we often also frequent destinations while we're moving around the city. We go to a market, we go visit friends on unplanned trips that we don't start from our homes, and we don't necessarily start from our workplaces. So I'll start by describing the sort of fixed origin metrics, some of which have been measured and mentioned in the previous sessions already. So something like a cumulative opportunities index, which simply counts how many destinations we can get to, would, for instance, quantify how many destinations of any character really are found within a certain walk range or transit time range. So this is, for instance, how many households or how many buildings, to be precise, are around a certain destination, like a coffee shop in an urban environment. This can be expanded to any type of destinations, of course. We can measure cumulative opportunities access to transit, businesses, jobs, residents, businesses of a particular type, residents of a particular type, and so on. And we can do it at all scales. So in this map, we use a cumulative opportunities index to measure across the United States in all cities how many people are found within a walk distance of a retail cluster. We did this analysis in all cities using all retail clusters around the country, and for instance detect that in New York City, across 5 boroughs, 88% of the population is within a kilometer of a retail cluster, and the cluster here is defined as an agglomeration of at least 25 stores. And if you're in Minneapolis, it's only 6%. On the map on the right-hand side, what black and white areas differentiate is areas that we consider to be urban versus suburban, and urban has a certain density cutoff. So with these sorts of indices, and as I think has been emphasized over and over again, what's really attractive is that they're very easy and clear to communicate. It's very easy to tell somebody that, look, 88% of the population in the city is within a walk range, and the walk range here is 1 kilometer or about a 15-minute walk. This could lead to really interesting policy applications too. So for instance, we did the same analysis for transit access across the entire United States, and we found that across the US, only 7% of the whole population lives within a walk distance from a transit station. This only considers rail transit, so it doesn't consider bus. At the same time, about 15% or double that rate is next to a retail cluster within a walk range. So it kind of evoked this idea of amenity-oriented development, where in places in suburban areas, especially where transit is lacking and nowhere in sight to be built, could we use this idea of trying to incentivize development to be close to amenity clusters, such as retail agglomerations or mixed-use service agglomerations, as a benchmark to incentivize more development around those. This slide also shows the cities that perform well or low on this axis. So In the first column is the percent of population within a walk range of a retail cluster, and the first group top is the high performers and lower performers are below. And what it sort of starts to also suggest is what sorts of cities they are, and how could we, through built form and planning regulation, incentivize certain characteristics of density and built environment that would lead to such qualities. So for instance, what we notice here is that they all have very high plot ratios, or FARs, floor area ratios in the US. They're also higher population density considerably, and they have typically higher built coverage. So these last three columns are mainly density indicators of different types, population density versus built density, and so on. Which would, if it's a goal to put as many people as possible next to retail agglomerations, then regulating density might be one option for doing that. And to calibrate such an index, you generally need origin points, destination points, optionally weights to describe what the destinations are, and some sort of a search radius parameter. The gravity type accessibility indices invented by Hansen in the 1950s are extremely popular, and I would argue somewhat more precise if we really want to talk about the notion of accessibility, because they also take into account the travel costs of getting to the destination. So the destinations that are next to us are weighted much more importantly than the destinations that are at the edge of the search radius we're looking for. Of course, the downside is that the result is a ratio and an index that's very hard to intuitively explain to a policymaker. What does it mean to have an index of 0.75 versus 200 jobs within a 5-minute walk? And in different cities, the decay rate that is applied in the gravity metric can differ. So this graph here shows a TRB study where they measured people's percent of people walking to transit in different cities. And as you can see, the decay rate differs by type of city, but also by income. So the top line is, for instance, Calgary, and the solid black line is, for instance, small communities in British Columbia. People are more sensitive to longer distances there. But we can calibrate this empirically by looking at a travel survey in a town, or conducting a small survey at transit stations and asking people how far you came from, and get a sense of what the distance decay rate is for that town. Using that index, then it's fairly simple at a very kind of fine grain to compute accessibility to various things. So this is some examples from the network analysis toolbox that we've produced and released free to use for everyone. This is at the individual building level accessibility to transit in Cambridge, where I work. Cambridge Senior, not Cambridge Junior, not the Cambridge Senior back in England, sorry. And it shows, it weighs different transit differently. So transit to subways is more important than transit to bus, etc. We can do the same thing to access to jobs, for instance, and we detect from every building how easy it is to get to jobs in town. And so this affects also kind of the likelihood of people who live in town to walk to jobs. And in Cambridge, the mode share of walking to work is actually very high. It's around 30% of people who actually walk to work rather than riding transit. This is another example of citywide transit accessibility at the individual building level. So this is in Singapore, where there's considerably many more buildings, and we also weighted the analysis by the level of service at each transit stop. And this, again, can be done to each address point individually. Now, the user inputs for gravity metrics, again, require origin points, destination points, optionally weights to describe the destinations, search radius, but also on top of that, a distance decay parameter beta that tells us how the likelihood of going to destinations drops away with distance. And this needs to be empirically calibrated. What I'd like to first emphasize before moving on is that what are the key planning and built environment features that affect either of these metrics? So I've talked about the cumulative opportunities metric and the gravity metric. So what could make a difference to upping that metric in different environments? First, if it's cheaper or easier to move to the destinations, if we have transportation options available from a building to destination, we can access more destinations, as I think Simon's presentation very clearly demonstrated in London. But there are three other ways in increasing accessibility. If we increase the density of destinations around the locations, the index would naturally also bump up. If we increase the capacity of the destinations around the location, the index would similarly bump up. And finally, if irrespective of the mechanized modes of transportation, if the built environment would be more connected around us, then we get to more destinations. So for instance, if you happen to have a hospital that's on a highly connected street intersection and many streets lead to it, it has higher accessibility than if it's in a middle of a block or in a location where not a lot of streets converge, irrespective of the mechanized transit modes that connect to it. And we can sometimes see about a 50% difference even within neighborhoods, that corner properties at the walking range render access to about 50% more people than in the same neighborhood properties in the middle of the block. But then there's the question of how would we go about measuring accessibility to destinations if we no longer assume that people come from a fixed location like a home or like a job? How could we take the attribute weights of those origin locations and somehow simulate as if people are moving through a city? And this is something that transportation modelers have long tackled, because every person is sort of simulated as if moving through a city during the day, and they can engage in activities from any point during those trajectories. But in accessibility studies, it's oftentimes actually ignored. Most of the time that I've encountered, we assume people coming from homes, every once in a while also from jobs, but not very often while moving around the city. So we've tried to tackle that issue by introducing a couple of new tools in the urban network analysis toolbox that help us model it at the pedestrian scale. If you think about an origin point, which is rendered as blue here, and a certain amenity that people might want to get to, then that amenity might look inaccessible or relatively far from an origin point if we assume that people go to there from home. But if the people on a routine basis, on a day-to-day basis, walk to some sort of a destination like a transit station anyway, then that amenity might happen to be right on that path, and it's extremely accessible to them. They just walk right past it every day. So we've proposed a metric that is based on the sort of betweenness centrality index known in network analysis and graph theory to redistribute weights from origin points to destinations in the city to simulate foot traffic on streets at the pedestrian scale. And we don't assume that people necessarily walk the shortest path, which actually turns out doesn't happen very often. A lot of pedestrian studies have found that we oftentimes go longer routes than shortest routes, so very often around 20%, 15% longer. So the tool that we developed also allows us to model all probable routes. So if we have, let's say, 100 people starting at the origin, then the same 100 people would finish at the destinations, but along the way there's a different probability distribution of which routes are more likely. And this is simply the way we do it. In this case, we actually assign an equal probability to every route, but because a lot of segments start overlapping, in this case there's about 64 routes here, those routes that overlap attain higher probabilities. And this is basically then we take the weight of the original building, which is 100, and every one of these points along the way gets a fraction of that weight, such that the sum of weights across all points still equals 100. So we're not inflating the number of people we assume to be on streets, we're simply redistributing it from one single point to a bunch of points on streets to simulate that effect. And this can be a way in which we model lots of trips in an urban environment that come from certain locations, like going from tube stops or subway stops to office buildings in the mornings, or from offices to subways or subways to homes in the evenings, or daycares, and all sorts of different trip destination matrices. To do this weights distribution, we need, again, origin points, destination points. Optionally, we weigh the origin points. So, for instance, we characterize how many people start those trips. And then we have what we call observer points, are these sort of distributed points on the network that capture the weights that we redistribute from the origins. And of course, there's some sort of a radius parameter. This can be scaled up. So I'd like to actually use this opportunity to demonstrate how changing the assumption where trips start can change in how we plan things in a city and what seems like a reasonable proposal for facility locations. So the first example comes from Singapore, and then I'll show you a second example from a context of Indonesia. So in this project, which was a collaboration with the Singapore Housing Authority, my lab, the City Forum lab at Harvard University, we were involved with developing a new planning norm for planning commercial facilities in Singapore's housing towns. And the same sort of housing authority, because they're so vast, in Singapore about 83% of the population lives in public housing, they therefore also have to cater to their commercial needs. So they actually plan commercial environments as much as they plan residential environments. And they sort of were tackling the problem of how to do that, where to put them, and what typologies of buildings to propose. So this map here shows the sort of the residential density. Every dot is a dwelling unit entrance. These are high-rise buildings. And so this is essentially the front door of a staircase, color-coded by how many units are upstairs. We used the approach I just presented to model how these households might be walking to transit stops on a daily basis across this whole town. This town has about 300,000 inhabitants. It's a big district of Singapore called Punggol. And so the transit stops fall into three categories. There is one single metro stop in that area, there's light rail stops, and there's bus stops, which are blue. Light rail is green. And so we calibrated a model that applied a certain probability to households to walk to each of those destinations depending on what was available around their house. So if the tube stop was available close by, then most of the trips would go to the tube. But if there was no tube stop within, let's say, I think this was an 800 meter cutoff, then trips would be allocated to light rail or bus. And the kind of balancing was, so we had a sort of an assumption matrix of how many trips would go where depending on how far these destinations are. But that essentially led to an estimation of the same people, the same 300,000 people in that town, now visualized or mapped according to their daily commute trips. In Singapore, 84% of the population uses public transit to get to work, so it's the most important travel mode for getting to work. And these trips can be assumed to happen across different social groups. And now, if we think that these are our origin points for planning facilities rather than the home fixed locations, we actually come to a very different plan for planning the facilities. If we don't put the retail centers, the food courts, the convenience stores into locations that are necessarily right next to people's homes, but rather right next to where they walk on a daily basis, we, turns out, actually capture much more demand. The accessibility results to retail destinations, the current existing retail destinations are shown with these black little circles here. This is measuring access to home locations, and this is to the distributed weights of the same number of people on city streets. If we actually looked at a related model where we use the accessibility indices to estimate how many people would visit what facility, then this here is the current built-out locations of retail destinations in that town. So every black circle is a retail cluster shown by square meters with the numbers. And we use the Huff model here. So for those of you who are unfamiliar, the Huff facility patronage model is entirely based on accessibility. So it's a ratio between the accessibility of one destination divided by the accessibilities of all destinations, and that creates a probability of going to that destinations. So each destination gets a certain probability, and all of the sort of demand is then somehow allocated between the destinations. So if we use the current model, I'm sorry, these numbers actually are not the sizes of the centers on this slide, but they indicate the number of estimated visits to centers, assuming that the trips starts from homes, and the total sum of visits under that assumption is about 33,000 trips during a certain period here. Now, if we just change the assumption that, say, let's model when the same people might make the trip on their walks to transit stops instead, we get a higher result. Now the result is 35,000 trips going to stores, simply because the stores appear more accessible to them on their walks to transit stops rather than coming from homes. So this kind of enforces the point that changing our assumption about where trips originate can also change the accessibility results and therefore alter how many people we expect to actually patronize urban amenities. So not only can the results change by bringing amenities closer to people, but also assuming from what locations people engage on those in those activities. When do they decide to go to a particular destination, in this case a retail cluster. Furthermore, we then developed a sort of scenario analysis to say this town was about half built during this study, and the authority, the HDB of Singapore, had already a plan for full build-out of commercial facilities. This is the full build-out proposal by them. And we said, actually, if we now assume that people could make those retail trips not from homes but on their daily walks to the MRT stations, would it also change where you would place the future facilities rather than keeping them where you plan them? And indeed, we discovered that by optimizing the locations of these facilities, by putting them closer to the walks, we could, in the full build-out, also substantially increase, it was about a 10% increase in estimated store visits by optimizing store locations next to people's walk routes. So this could both improve accessibility to people if we operate this way, but it also would actually make more stores viable because they would have probably more visits on a daily basis. And so there were proposals of how to kind of, along that same mode of thinking, to move away from this sort of a single building destination model. So the HDB is currently planning a lot of retail centers like single building malls that you just walk to from your home, to rather lining streets with commerce on your daily walks to the MRT stops and distributing it along streets as a different typology. A second example of applying this distributed modeling using the betweenness index comes from Indonesia. And this is a study we did with the World Bank on an MRT corridor in Indonesia. So the city had already laid out a plan for a first light rail in Surabaya. Surabaya is the second largest city in Indonesia. This was their first transit system. And they already marked down where the stations should be and developed a sort of alignment for the line. So we were not asked to kind of change the stations, but rather to develop a TOD strategy, a transit-oriented development strategy around those stations along the line. So what we did was use similar tools. We analyzed population density around every one of these stops. So this is at the sort of census block equivalent level in Indonesia. These are called RTs in the local context. And then we used a similar approach as I showed above for routing trips from homes to stations. So there's a sort of probability distribution as they move through an environment. They come from a certain home and go to their nearest station, but there's a probability distribution, not just the shortest route for going there. And we then did it across all several thousand census tracts, and by doing that detected which street segments in the environment would be most critical for providing access to the future tram system that was proposed. And we argued that it's absolutely vital that those streets be in good shape for the system to work. That and when I say in good shape, we come from a very different standpoint in Paris or London and in Surabaya. It's customary when it rains that streets flood in Surabaya. There's generally no sidewalks. And what we discovered also in the sort of demand analysis was that the most likely demographic for this new transit line would be women and children who don't have cars or scooters. And if you have a car in Surabaya, you probably drive your car. It's a status symbol as much as a transportation device. So, but those who don't generally are women and children. And those are especially vulnerable groups for accessing the tramway. So for instance, if you go with your child in the tram and the street is completely flooded, there's 2 feet of water on it, there's no chance that this system would attract a lot of ridership. And from that, we filtered out, there was a lot of paths, of course, in the full analysis. We filtered out those segments that are absolutely critical, where we had the highest estimates of pedestrian footfall for getting to the stations, and then proposed an improvement program on top of that. But before I showed some of the improvement slides, I wanted to mention, once we have an estimate for how many people we think are going to use a segment per day or per hour then this number is somewhat abstract to policymakers oftentimes. So what does it mean that we have 250 pedestrians per hour on a sidewalk? Most people don't really know what that feels like. So we developed a related tool, which we call a street catalog, where we filmed with time-lapse videos streets around the world and measured their pedestrian densities, and also provided some general indicators of what's around there with accessibility indexes. So for instance, how many transit stops, how much density, how many jobs are around these streets, to give some context to what we're seeing. But so, for instance, on this slide, there is a street that has a pedestrian density. If we can start. Should I go back? I think Montserrat is trying to start that video button on the bottom. So this is a 12 times faster than normal speed time-lapse video, and this is 904 people per hour kind of street. So we just wanted to develop benchmarking tools, a catalog of streets from around the world, from different cities, where a person who sees an estimate number of 200 people per hour on a sidewalk, what does it mean? What does it feel like? And by filming streets in China, in Europe, in the US, we've tried to populate that catalog to give that some intuition, some sense to a policymaker what that might feel like. So that's, we can go next. Can we go next? Or stop from the bottom? This doesn't override it. This doesn't override it. Can we just click next? Okay, so the catalog has different cases of that. And so along the same lines in the Surabaya project, we just, for those links that were deemed as the most important future walk routes to the planned transit stations, we proposed that the city initiate a series of upgrade projects ranging from putting in better paving, bike lanes, rezoning some of the properties along those to have active street fronts, street furniture, landscaping, drainage, lighting, and so on. Now, finally, in order for us to actually engage in such analysis and for cities to do analysis at that level of detail, we typically need different types of data than what is available. And if we look at a place like Oxford Circle in London, most cities, and I'm sure London actually has better data than what I'm showing here, but most cities will have road network data here. And at best, they might also have some estimates of how many cars per hour at peak hours are on different segments here. But the things I've been talking about are entirely outside of this data. They're here on the sidewalks and around the amenities and destinations that are along those sidewalks. And a lot of cities, in fact, the vast majority of cities do not maintain a database on sidewalks, but simply assume that pedestrians walk along road axes. So we oftentimes end up surveying this data ourselves, but this is not scalable. For us to kind of really implement pedestrian-scale last-mile modeling in cities across the country, we need a more institutional approach to data collection. And furthermore, we need to know a little bit about what happens on those streets. So we recently started a pilot project at Harvard in collaboration with the engineering school, where we're trying to use computer vision techniques to describe what happens on sidewalks. So rather than simply counting how many cars a street has, which is the number that most cities will bring to a policy discussion about what should we do with the street. The street has 1,000 cars per hour. Could we use computer vision techniques to actually measure what happens on streets in totally anonymous ways, just simply by feature recognition? See how many pedestrians were on the street, how many people were standing, talking, or pushing a baby pram, how many cyclists, and also including the traffic measures of buses, trucks, and cars. This is entirely feasible. There's a commercial company out there already doing this, but cities sort of have not fully adopted it. The data would be extremely valuable for pedestrian level analysis to understand what actually happens on those sidewalks and streets throughout the day. And that could be major for policy input as well. So if we look at, for instance, a country like the US, we'll have excellent road network data. The census collects it, called Tiger Road Networks, and you can go and download it for any place. It's detailed with lots of attributes. We don't have the same for sidewalks, and many cities are starting to realize that. For instance, Denver has been going through a big effort to become a more pedestrian, less car-oriented city, and they think that a major barrier towards that end or towards that vision is really the lack of data. The city can't improve its walking network if it doesn't know where the weaknesses are, and yet no city department has any inventory of sidewalks or crosswalks. And I think that this is actually a fairly low-hanging fruit for or worthy fruit to pursue for both cities to start doing mapping of sidewalks. It's actually being done by grassroots organizations now. There's crowdsourcing platforms for collecting sidewalk data. This is an example from Denver called WalkScope. So they just engage a lot of volunteers to help the city map where the sidewalks are. But again, that's something that's pretty hard to institutionalize and scale. So why can't we have city governments collect sidewalk data with equal precision? And of course, we need to come up with a certain standard of how this needs to be documented. And I would also think that if OECD helped make a suggestion to cities that this is good, then I think that would be extremely helpful to a lot of pedestrians around the world. And there's, for instance, the city government of Singapore, we managed to convince, is now collecting pedestrian sidewalk data and overpass and underpass data they're officially putting it together. But I think it would be great to do it at large. So just a couple of conclusions. I started arguing that most of the accessibility indices assume trips coming from fixed locations, generally homes, but that's not oftentimes the case, especially in big cities. We have very complex trip chains, and oftentimes we engage in activities not from a fixed location like home. So therefore, we probably also should not be planning amenities in the cities just to be close to homes. And changing that assumption will change where it makes sense to place facilities. It actually leads to a different result when we assume origins to be different. And when talking about pedestrian accessibility in that sort of last mile scale, that it's important to start focusing on streets and their attributes that we actually don't have. So having data at the sidewalk level. And Simon was earlier touching upon the question of step-free access to buses in London, and we briefly chatted afterwards, but I sort of highlighted the point that we might have a step-free bus, but the walk to the bus might not be step-free. And we don't know that if we don't have pedestrian-scale data. If it involves going down steps and up curbs, and there's no way you can roll a wheelchair through that, or sometimes even a baby pram. So needing pedestrian sidewalk data also requires some of these attributes. We really have to be very careful to observe level changes in that data. And I, again, would love to talk to OECD about coming up with those standards and making those recommendations to cities. And finally, I'd like to say, sort of as an urban planner who works a lot with accessibility indices, that in my work, I encounter that the analysts and the planners are oftentimes very different groups of people. And I feel like it's very beneficial, and this is partly why we've been developing our tools as plugins for GIS and as plugins for Rhino, which is a software a lot of designers use, to put the analytics at their fingertips so that when you're designing a plan, you could run through scenarios yourself with just a few clicks without needing to kind of come up with a complex plan and hand it off to analysts who come back 2 weeks later and say, this works, this doesn't. There's very little project adjustment that can happen with such small or slow feedback cycles, and making sure that analysts are also engaged in the design process more, I think, is vital. And I think we can, similarly as we can analyze existing urban environments with accessibility indices, we can perform the same analysis in scenarios as been already shown. So scenario A, B, C for future, and evaluating project qualities based on future street layouts, future urban environments that we plan, not just the ones that already exist. So with that, I'd like to thank you, and there's a few articles that relate to this work.